Hey everyone, it's Justin again. In this lesson, we're going to be learning about composite surface area. You're going to be using all of the surface area formulas you've learned so far in this unit, so make sure you have your notes on prisms, cylinders, pyramids, cones, and spheres on hand. By the end of this lesson, you will be able to find the composite surface area of figures made up of prisms, cylinders, pyramids, cones, and spheres. First, we'll discuss composite surface area, and then we'll complete 2 example problems. So, what do I mean by composite surface area? Well, do you remember what a composite figure is? We first talked about these back in our area unit. Exactly. A composite figure is a figure made up of multiple shapes. So, in this case, by composite surface area, I mean the surface area of a figure made up of multiple 3D shapes. There's a little bit more to this than just finding the surface area of different shapes and adding them together, though. For example, if I combine a pyramid and a prism, the surface area of the composite figure that they create is not just the surface area of the pyramid plus the surface area of the prism. Why not? Well, what do you see in this figure that makes it so that its surface area is not equivalent to the surface area of the pyramid plus the surface area of the prism? Yup, it's this part right here. This space that is the base of both the pyramid and the prism is now not even a part of the outside surface of this new composite figure. If I were to wrap this composite figure in wrapping paper, I would not even be able to get paper on this part of the figure. Instead, the surface area of this figure would be the sum of the area of all of these faces. Don't worry, we won't have to calculate the surface area one face at a time. We'll still be able to use our surface area formulas, but we will have to be careful about which parts of each formula we use. Let's try it out so that you can see what I mean. Our first example problem says, this composite figure was created by attaching a cone and a hemisphere to each base of a cylinder. The bases of the cylinder and cone have a radius of 7 inches. What is its composite surface area rounded to the nearest tenth? There's a new word in here, hemisphere. Based on the context clues on screen, what do you think a hemisphere is? Maybe you noticed this little bump on the composite figure. A hemisphere is half of a sphere. So there are 3 parts of this composite figure. The hemisphere, or the half of a sphere, the cylinder in the middle, and the cone. Our composite surface area will include some parts of each of these 3. Let's start with the cylinder. This is our formula for the surface area of a cylinder. Remember, big B represents the area of one base, big P represents the perimeter of the base, and big H represents the height of the cylinder. In terms of the cylinder, what does this whole term 2 times big B represent? This is the area of both bases combined. Take a look at our composite figure again, and specifically, look at the bases of the cylinder. Imagine you were wrapping this figure in paper. Are the bases part of the surface area? Are both of them part of the surface area? Just one? Neither of them? Neither of these bases are on the outside of this figure anymore, so we could just get rid of this term. How about big P times big H? What does this represent in our cylinder? This is the lateral area of the cylinder. So the area of the curved surface between the 2 bases. Is this part of the surface area of the composite figure? Is all of it included? Just some of it? The entire lateral surface should be included in the surface area of this composite figure, because none of it has been covered up by adding on this cone or hemisphere. So the surface area of our cylinder that is included in the composite figure can be represented by just big P times big H. Pause the video now and fill in this expression using the given information for the cylinder. The problem tells us that the base of the cylinder has a radius of 7 inches. The perimeter, or circumference, of a circle is calculated by multiplying 2 times pi times the radius. I can replace big P with 2 times pi times 7. The height of the cylinder is shown here, and it's 16 inches. So this expression will represent the surface area of this composite figure that comes from the cylinder. Like always, we're going to wait to put this into our calculator until the very end. So for now, I'll tuck it away up here for safekeeping. Now let's take a look at our hemisphere. The formula for the surface area of a whole sphere is 4 pi r squared, where r is the radius of the sphere. But we don't have a whole sphere in this composite figure. How do you think we can change this formula to account for the fact that we only have half of a sphere in this figure? Did you guess that we could just multiply this by 1/2? Nice job. If we take half of this formula, that would give us 2 pi r squared. What do you think the radius is for this hemisphere? Yes, our hemisphere has the same radius as the base of the cylinder, so r is 7. Now all that's left is to figure out the cone. The formula for the surface area of a cone is big B plus 1/2 big P times lowercase cursive l, which is the slant height of the cone. What does this term big B represent? Yep, just like before, it's the area of the base. Should the base of the cone be included in the surface area of this composite figure? All of it? Part of it? Just like the bases of the cylinder, the base of the cone is no longer part of the outside surface of this figure. So we won't need this term at all. What does this whole term represent? In all of the surface area formulas, the terms that involve big P will always represent the lateral area or the area of curved surfaces. In this cone, that would be this curved surface here. So should this be included in the surface area of the composite figure? Yes, this entire curved surface is still part of the outside of this figure. So this expression represents the surface area that the cone contributes to the composite figure. Since the base of the cone is the same as the base of the cylinder, big P is still 2 times pi times 7. What's lowercase cursive l, the slant height of the cone? The slant height would be 11 inches. So this expression represents the surface area that the cone contributes to this composite figure. Now that we've found how much surface area the hemisphere, cylinder, and cone are all contributing to the composite figure, we can take this whole expression and put it into our calculators to get a final answer. Go ahead and do that now. Your calculator should give you back this decimal approximation. When we round to the nearest tenth, our final answer is 1,253.5 square inches. Our second example problem says that the composite figure was created by removing a pyramid from a prism. The bases of both the pyramid and prism are regular pentagons with an apothem length of 4 centimeters, and the pyramid has a slant height of 10 centimeters. What is the composite surface area? Since this figure has 2 shapes overlapping, it might be harder for you to visualize. So let's try using some colors to help. Here's the prism, and here is the pyramid going inside of it. Even though it's inside of the prism, the pyramid does affect our composite surface area because this shape is not solid all the way through. By removing that pyramid, we've created a hole, a hollow area. Imagine it this way. If we were to flip this shape upside down, the pyramid creates a well that we could fill with something, like water. So now that we understand what's happening with this figure, try imagining that you have it in your hands. All of the places where you can touch are surfaces that count towards the composite surface area. There are 11 total faces that we need to count toward the surface area here. Pause the video and try to identify all 11. From the prism, we have this face and all 5 lateral faces. The second base, which would be here, has been removed. From the pyramid, we have all 5 lateral faces. Its base is also not here because that opening is what creates the hollow space inside of the prism. Okay, now we have a better understanding of what's happening with this figure, so let's try to find its surface area. Start with the prism. Here's our formula for surface area of a prism. Pause the video here to identify which parts of this formula we'll be keeping to count towards the composite surface area. This term represents the area of both bases of the prism, but we only have one base left. So instead of 2 times big B, we should change this term to just big B. This term represents the lateral area of the prism. All of the lateral sides are still part of the composite figure, so this term will stay as big P times big H. If you haven't yet, go ahead and fill in this altered formula with the measurements of the prism. Using what we know about regular polygons, and that the height of this prism is 9.2 centimeters, here is what we get for the surface area that the prism contributes to the composite figure. Let's make note of this up top, and then move on to the pyramid. Here is our formula for the surface area of a pyramid. Pause the video now to identify which parts of this formula we'll be keeping to count towards the composite surface area. This term represents the area of the base, but the base is not present here because the bottom is hollow. That means we need to just get rid of this big B entirely. This term represents the lateral area of the prism. All of the lateral sides are still part of the composite figure, so this term will stay as 1/2 big P times lowercase cursive l. Go ahead and fill in this altered formula with the measurements of the pyramid if you haven't already. The perimeter of the base is the same as it was in the prism, and the slant height was given as 10 centimeters. This expression represents the surface area that the pyramid contributes to the composite figure. To find the total surface area of this composite figure, now all we have to do is just add these together. We can put this whole big expression into a calculator to get our final value. Pause the video and do that now. Your calculator should have given you back 469.8. Make sure you add your units label of square centimeters, and then you got our final answer. When finding composite surface area, start by identifying which faces of the figure contribute to the surface area. Then, determine which parts of the appropriate surface area formulas you need to use to find the area of those faces. Fill in your altered formulas using the information from the problem, and lastly, add together the surface area that comes from each individual 3D shape to find the total. Don't let the wording confuse you. If a shape is removed to create the composite figure, it is still going to add positive surface area. Keep all of this in mind while you work on your practice. Good luck, and I'll see you next time. Hey.